Hello guys and welcome to another calculus video. In this video we are going to be starting off the integration guide series, and this is going to be part 1 of 4 for our videos on contour integration. So we're going to be covering everything about contour integration right from the very basics. The only thing that you need to know for this video is the basics of the complex plane, what is a complex valued function, and how to calculate complex exponentials and complex logs. You don't need to know any very in-depth complex analysis because we're going to cover all of that in this series. So if you already know a lot of complex analysis, maybe you'll want to skip to the next video. But anyway, I'm really excited to start this series, so let's go ahead and get started. So the first thing we need to cover is what exactly is contour integration. I mean, it's definitely not the same as normal integration, and you'll see why. So I have here the real and complex analogs right here. As you can see, our real integral can be stated as the integral from a to b of f of x dx. And so what that looks like if we drew a number line is just like this. We're starting at point A, we move, as these arrows indicate, to the right from a to b. And we're adding up all the values on this line, and we're also multiplying by dx. So dx is obviously a real number in this situation. However, this is what a contour integral looks like. And you'll notice that I put a little c right here, and that indicates that that's the curve over which we're integrating. So this is a curve that we call curve C. Also, you can see this little circle on the integration symbol, and that just means that our curve C is a closed curve, meaning it starts and ends at the same point. So this is our curve C, and as you can see, we're integrating f of z dz over this curve, which means that we're adding up all these different points. However, something that's actually different from normal integration is that our dz value is not just an infinitesimally small number, it's also a complex number as well. So you can see dz equals dx plus I dy if x is our real part and y is our imaginary part. So x and y are real numbers, but dz is a complex number, which just indicates the difference jumping from one point to another. Also, conventionally, contour paths are almost always going to go in a counterclockwise direction. So if the direction isn't specified on anything, you can always go ahead and just assume that they're going to be oriented counterclockwise. Now we can also have non-closed contour paths, and those are not going to have this little circle here, but they'll still have an indicator of the curve that they're on. So here's a more formal definition of our contour integration. So if we have a curve, which the classic Greek letter to use for that is lowercase gamma. So if we have a curve that is lowercase gamma, then the contour integral over that curve, notice that we don't have a circle here because, again, gamma does not necessarily have to be closed, is defined by this limit. And if you're familiar with the limit notation for normal integration, you'll notice that this is just the integral from 0 to 1 of f of gamma of t times gamma prime of t dt. And so if we were to substitute u equals gamma of t, then that would essentially just give us the integral from the starting point to the ending point, right? So gamma of t is just tracing out the curve gamma of 0 and 1. Now this limit notation isn't necessarily very important to us, but it is important to understand, the basics of how we are defining things when we get into the more hairy sides of contour integration. So one thing that this does actually mean is, first of all, if we have multiple curves which add up to become a third curve, in this example we have this curve gamma 1, which is on top, and this another curve gamma 2, which is on the bottom. You can see that if we add these curves together, we make a third curve that starts from this point, goes all the way around, and then ends right here. And so if we call that gamma 3, then the integral of f of z dz over gamma 1 plus the integral of f of z dz over gamma 2 equals the integral of f of z dz over gamma 3, which is pretty straightforward. I mean, just think about it. If you have the integral from a to b of f of x plus the integral from b to c of f of x, it's the same as the integral from f of x from a to c. So that's essentially the real analog right here. So I have some practice problems if anyone wants to try to use the limit definition here. I'm going to have a lot of practice problems throughout this series just to check your understanding so that you can know if you're all caught up. So practice problems right here are to use the limit definition of a contour integral to calculate the integral over gamma of just dz. And so we have 3 different examples here. In example 1, our curve gamma goes from z equals 1 minus I to z equals 1 plus I in a straight line. And then you can read these starting points and ending points for these other curves. And this curve goes from this point to this point. I didn't put the arrow there. So if you want, you can try these practice problems, but the limit definition is not necessarily the most important thing. So if you don't want to try that, that's okay. One other thing we have to cover is most importantly, I think, in this video, is why do we do contour integration? After all, we are literally making the integral more complex. So why are we going to do that? And the reason for this is that the integral is more complex but easier. And I have this little, we'll cover this formula quite in the next video, I believe, but you can see that this integral actually just turns into a sum, and this is actually not even an infinite sum, it's a finite sum that you can just compute by hand. And this residue actually represents a limit. So we take a contour integral. Now, integrals are really hard to solve, especially if they don't have an elementary antiderivative, and we just turn it into a limit. And that is the whole point of complex integration. Complex integration is incredibly easy to do because integrals just become simple limits. And if we can combine our knowledge of complex integrals and real integrals, we can solve real integrals much more easily. So one other thing we have to cover right here is simply the fact that simply an anti-differentiation here. So f of z is an antiderivative of f of z, capital F for the first one. Same thing as with real integration, the integral from a to b of f of z dz is capital F of b minus capital F of a. Pretty straightforward. It's the same thing as real integration. Now, this is actually not too important to deal with because we are almost never going to have a situation where this is useful to us because we pretty much only deal with functions that don't obey this rule or don't have an antiderivative. So this is not really something to worry about right here, but it's just a statement that might be handy to know. So now we're going to discuss the topic of analytic and holomorphic functions. Now, technically, analytic and holomorphic have two different definitions. I have this image from Wikipedia right here that you can see. A holomorphic function is defined by a function that is complex differentiable. So that essentially means that you can take the derivative in the complex plane, and that means that the derivative, no matter which direction you go, like you could go in the positive direction, in the negative direction, in the I direction, in the negative I direction, or in any other direction in between, at any angle, the derivative is going to be the same. That's what complex differentiable means. And analytic means that a function is locally equal to its own Taylor series, or in some cases, Laurent series, which we will discuss later. And a fundamental assumption of complex analysis is that if a function is holomorphic, that function is also analytic. So we can use these definitions sort of interchangeably. And the good thing for us is that most functions are actually holomorphic. So for example, z to the n, sine of z, and e to the z. And anytime we compose any of these functions with each other, we add them together, we divide them or whatever, our function will still be completely holomorphic. So that's very nice. In general, most functions are going to be holomorphic that you look at. The only exception to this, well, there are a few exceptions, would be at singular points. So a singular point is essentially where a function diverges to infinity, usually when you have a zero in the bottom or some other similar situation. This doesn't include removable singularities. So if a singularity is removable, for example, sine of z over 0 at z equals 0, then that doesn't count as a singularity, and our function is going to be analytic at that point. So here are some examples of points where certain functions are not analytic. So 1 over z squared is analytic everywhere except at the point z equals 0 because it has a singularity right there. 1 over z squared plus 1 at z equals plus or minus I, sine of 1 over z at z equals 0 because again of that singularity, and cosecant of z at z equals n pi for n is an element of the integers. So that just means that this has infinitely many discontinuities or singularities, and those are all points where this function is not analytic, but everywhere else it is analytic and holomorphic. The only exceptions to this rule is essentially going to be weird functions like modulus of z, or absolute value of z, however you want to say it, and z bar, which is the complex conjugate of z. These are holomorphic and analytic nowhere in the complex plane because of the way that they act. They're just not. They're not normal functions, essentially. And the functions natural log of z and z to the p, p just representing power, where p is not an integer, these are going to have what are called branch cuts, which means that they're analytic in most places, but there is a large section of the complex plane where they are not analytic, and we will discuss those later. So now that we know what an analytic function is, there will be some practice problems at the end of the video if you want to go try those now, but now we're going to discuss Cauchy's integral theorem. And Cauchy's integral theorem essentially states, if f of z is analytic in some domain, then for any simple closed curve C in the domain, the contour integral, closed contour integral, over c of f of z dz equals 0. Now, I've removed most of the math terminology from this definition to make it a little bit more straightforward, but if we want to remove even more, the basic statement is that if f of z is analytic everywhere inside of the curve c, so for example, in this case we have our curve c1, so everywhere inside of this curve and everywhere on this curve, so everywhere where the red line is and everywhere inside of the red line, if it's analytic in all those places, then we can state that the contour integral is going to be equal to 0. And the same thing with c2 here. This is our domain right here where the function is analytic on everywhere inside the circle. So the integral over c1 and the integral over c2 are both going to be 0 because these are both closed curves. So that's a very, very powerful statement, and it's the formation of much of contour integration. Now, there are going to be some practice problems on this, but there are also some other topics that we have to discuss here. There's something called contour deformation, and this is another very important topic. Now, these x's right here represent poles or singularities of the complex function. So that means that within this domain here, our function is not analytic, which means that the integral of f of z over c1 is not necessarily 0. We can't calculate it. We don't know what the value is. But a statement that we can make is that the integral over c1 is the same as the integral over c2. And the reason for this is everywhere inside c2 is the same as c1, and I'll show you what that means in a moment. Let's imagine a third curve, c3. Now, c3 looks a lot like c2. It has this outer circle, right, that matches up exactly like c2, and it has this inner circle that goes counterclockwise here, while c1 actually goes clockwise. So essentially, since these integrals go in opposite directions, it's like integrating from a to b or b to a. It's just going to be a minus sign. So if we add c1 plus our function, plus our curve c3, the integral over c1 and the integral over c3, we get c2, because this just ends up subtracting this one. However, also, we can argue that the contour integral over c3 is going to be 0. And the reason for this is, as you can see, we have, we're encircling this area right here. Since this is going clockwise, c3 actually goes in the negative direction. And then this inner curve goes in the positive direction. And what this essentially causes to happen is that the only area that's actually counted is this area in between them, which is a little bit of an interesting situation. So this area in between is actually what counts as inside the contour. And so that can be very useful for a lot of different types of contour integration, and it's going to be the formation of the residue theorem, which we'll learn in the next video. So that means we can argue that the integral over c3 equals 0, which means that the integral over c1 is the same as the integral over c2. So if we have a function that's analytic except for a set of certain points, any curve which encircles the same set of those points is going to have the same value, as long as we're going in the same direction. So if we flip the direction, if we went, one of them went counterclockwise and one of them went clockwise, then they would have, then the value of one would be negative the value of the other. So contour deform is something very important to understand. So if we deform the contour, essentially we change the shape of the contour, but we have the same points inside of the contour, then the integral over that contour does not change. Okay, let's move on to our next topic. Oh, yeah, so one way to sort of internalize the meaning of the Cauchy's integral theorem, which looks kind of weird. I mean, the integral over a closed curve of an analytic function is 0, is when you have a closed curve, think about it. You integrate, you start, let's say we start right here, and then we go around this curve, right? Oh, sorry about that. We go around this curve, go through this little bend, we come back, and then when we close the curve, we end up at the same point. So it's almost like when we integrate over the real line, if we were to integrate from some point A to some other point A. And of course, that's going to be 0. So that's a sort of reasoning that you can put to explain why the integral over a closed curve C is going to be 0 for an analytic function. But that's not always going to be the case. This is just a good way to sort of remember when contour integral is going to be 0. One other thing I want to note is that the definition does say a simply closed curve in closed curve C, and what that means is that our curve C can't intersect itself, so we can't have like loop-de-loops or like multiple curves that like cross each other, that's something that we can't deal with, but it's not something that will ever be useful to us anyway. So a simply connected curve can't intersect with itself. And that's pretty much it for this video. I'm going to have my Discord open, hopefully, so you guys can go join that, and if you have any questions on this or anything that you want me to explain further, I'll be available in the Discord right there. But for now, we have some practice or homework questions that I would absolutely love for you guys to try just to check your understanding and to make sure that you understand everything. So first, we have a practice on analytic functions, where you just have to find the singular points of f of z. Now we're looking at analytic functions, so these points will be the only points where our function will not be analytic. So here are 3 different values of f of z. C is a little bit more difficult, but I'm sure you guys can figure this out. So go ahead and pause now and try those problems. Problem number 2. We're going to choose all of these functions and we're going to classify them as analytic everywhere or nowhere, remembering that certain functions are analytic everywhere, certain functions are analytic nowhere, and whenever we compose those functions, they'll pretty much take on the same, they'll pretty much have the same behavior as the inner function, right? So go ahead and classify as all of these functions analytic everywhere or analytic nowhere. And last of all, we have our practice problems on Cauchy's integral theorem right here. Now, this is some notation that I want you guys to learn. When we have this notation right here, I actually forgot the contour integral sign here, but that's okay. Where you see like absolute value or modulus of z equals 1, that's just saying the curve oriented in the counterclockwise direction of all the points where the modulus of z equals 1. So if you imagine the modulus of z equals 1 in the complex plane, that just means all the points where the distance from the origin is 1. So it's a little circle of radius 1. And same thing right here, z minus 2i, that would just be all the points that are a distance of 1 from the point 2i in the complex plane. And again, these should have close, the path will always be in the counterclockwise direction if it's not given to you. So in this case, it's not given to you, so you know that the path is going to be in the counterclockwise direction. And then for problem 3, you're going to tell me which of these integrals can be calculated using Cauchy's integral formula. Reminder that a function has to be analytic everywhere inside the contour to be able to use Cauchy's integral formula. So go ahead and pause and try these 3 problems. And once you've done that, I'm just going to go ahead and say there's a lot of stuff that we're going to be covering in the next video, so please look out for that one. We're going to be covering the residue theorem, Laurent series, calculation of residues, essential singularities, and branch points and cuts. So hopefully you guys are ready for that video, and yeah, look out for it. It should come out about 2 days from this video. Yeah, hope you guys enjoyed the video. Please leave any questions for me in the comments or in Discord, and I'll see you next time. Hello guys, and welcome to another calculus video. In this video, we're on video 2 out of 4 on our. So in this video, we're going to be covering Laurent series, residues, and the residue theorem, which are all very, very important in the calculation of contour integrals. So let's go ahead and jump right into the lesson. So first off, we have to discuss what is a Laurent series. So when we're dealing with real numbers, we'll generally use what's called a Taylor series, which is just a series of terms multiplied by powers of x minus x0, where x0 is the center of the Taylor series. And these will have a radius and interval of convergence and all the sorts of things that we're used to. However, when we get to complex analysis, we actually use something else we called the Laurent series. And the reason we use this is so that we can choose our starting point for the series to be anywhere we want, even a point that has a singularity. And so a Laurent series will have it'll have a Taylor series, first of all, within the Laurent series, and it'll also have terms of negative degree. Now these terms of negative degree, when you add them all together, are called the principal part of the Laurent series, and they are very, very, very important. So the Laurent series will start at some Bn, and that Bn will correspond to the order of the pole at which we're doing the Laurent series. So for example, if we wanted to calculate the Laurent series of 1 over z at z equals 0, then the Laurent series would just be 1 over z, right? So we have a first order pole, and our first term is just going to be b1. However, if we have a more complicated function, like for example 1 over z squared with z minus 1 to the third power in the bottom, then if we wanted to create the Laurent series around z equals 1, we would have a b3 term, and then a b2 term, and a b1 term, and so on and so forth, right? So the first term, or the term of the highest negative degree, is going to correspond to the order of the pole. Some Laurent series may have an infinite number of terms of negative degree, and this is called an essential singularity, which we'll get to later in the video. And most importantly, the residue of the function of a function f of z at the point z0 is just the coefficient of 1 over z, which is the same as b1. So this number b1 is super important in complex analysis, and it is called the residue of f of z at z0. So of course, we can calculate the Laurent series of a function at many different points. So the residue is not a value only of the function, it's also a value that's dependent on the point at which you're taking the Laurent series. So one function may have multiple residues. So why do we care about residues? I'm going to show you why residues are so important. We're going to consider a contour integral over a curve gamma of f of z dz. This is a closed contour. And the point that we're worried about here is we're going to center our contour integral about a pole of some function. And we're going to let our radius of this circle, which makes up the curve gamma, be r. And this is going to be a perfect circle. One important thing is that this radius r is small enough such that our this pole is the only pole or singularity of our function that falls within the circle, right? So this r can be arbitrarily small or large as long as it satisfies that requirement. And this is the point z equals z0, which is a pole of the function, as I said. And interestingly enough, we can actually describe this circle by z equals z0 plus r e to the I theta. So we're centered at z0, we're r distance away from the center, and e to the I theta is just going to trace out a nice little circle because of the trigonometric properties of e to the I theta. And so theta is going to go from 0 to 2 pi. And what this means is that we can actually use this expression. Since theta is going from 0 to 2 pi, we can convert this contour integral into a normal integral. So if we calculate dz dependent on theta as our variable, we get that dz equals I r e to the I theta times d theta. Sorry, I missed that d theta in there. I was going back and checking. So this is all d theta. And then we're going to use the representation of f of z as the Laurent series. So I just have a and bn have been combined to just be cn, as n goes from negative infinity to positive infinity. So when we go ahead and substitute this in, this looks very daunting, but we're just going to go step by step. We've taken the summation outside of the integral because we're just considering the effect on each of the individual terms. So we get cn times the integral from 0 to 2 pi of r e to the I theta, which is just z minus z0 to the n, right? All raised to the n power plus I r e to the I theta d theta. Then once we separate the r's and the I thetas, we're going to get this. R to the n plus 1 times I e to the n plus 1 I theta d theta. Then when we integrate this with respect to theta, as long as n isn't equal to negative 1, because if n is equal to negative 1, then we just have e to the 0, right? So let's not consider that one right now, but for all the other values of n, we're just going to end up dividing by n plus 1 times I and evaluating it at 2 pi and 0. And what this means is that this term is actually, all of these terms except for the negative 1 term are going to go to 0, because when you evaluate this function right here at 2 pi and at 0, because theta is 2 pi and theta is 0, and this is just an integer, where it's going to be a multiple of 2 pi, and e to the 2 pi I is always just going to be 1. So it's going to be the same at both bounds, and so it's going to be 0. However, for n equals negative 1, we're integrating I times d theta from 0 to 2 pi. And of course, we also have this coefficient c negative 1, which, as we know, is the residue of the function at z0. And when we integrate I d theta from 0 to 2 pi, we just get 2 pi I times c negative 1, which is the same as 2 pi I times the residue of f of z at z0. And this is incredibly helpful because the residue can be calculated without calculating the integral, which makes the integral much easier to calculate. And this leads us directly into the residue theorem, which is the basis of most contour integrations. So the statement of the residue theorem, this is a shortened version, but it's the only version that we're going to actually need. If gamma is a positively oriented, meaning it goes in the counterclockwise direction, simple closed curve, then the contour integral of f of z dz over gamma is going to be equal to 2 pi I times the sum of all the residues of f of z at points zk where zk is all these singular points inside of gamma. So if we have some closed curve, all we need to do is find all the singular points, find the residues of the function at all of those points, add them together, and multiply them by 2 pi I, and that gives us the value of the contour integral. Also, simple closed curve does also require that the closed curve does not intersect itself, so that's important. So let me go ahead and show you it's not necessarily a proof, but just a demonstration to how this actually works. So we're trying to calculate the integral over this curve gamma, which I've just made a circle of f of z dz. It has some residues on the inside here. So the way we're going to do this is we're going to consider a second curve, gamma 1. Now, gamma 1 is the same as gamma. It has this counterclockwise oriented circle right here, and it also has these clockwise oriented circles around each residue. And these circles can be made as small, as large as you want, as long as they only enclose the residue and no other residues or singular points nearby. Or sorry, not residue, poles. They only enclose those poles and no other poles nearby. And based on what we talked about last video, since these are negatively oriented, or they go in the clockwise direction, we actually only count all the area outside of them. So we're counting all of the area inside of this outer curve, but outside of these curves. And since our function has no poles, and we're only dealing with analytic functions here, then since everywhere in this area is analytic, since we're not dealing with the poles right now, by Cauchy's first theorem, or Cauchy's integral formula, which we discussed in the last video, this entire integral just goes to 0. So this gamma 1 integral goes to 0. Then we also consider this gamma 2, which is this curve where it's pretty much just the opposite of these three circles, it going in the clockwise direction around each of these poles. Now notice, if we add the integral over gamma 1 and the integral over gamma 2 together, we just get gamma again, because positively oriented, negatively oriented, they cancel with each other. And we can split up gamma 2 into these three separate integrals of these small circles, and they're actually the exact same integrals that we calculated earlier. It's just a small circle around a residue, or around a pole, sorry, which is just going to be 2 pi I times the residue of the function at that pole. So that means that our entire contour integral, which remember was the integral over gamma right here, is going to be 0, which is the contribution from this integral, plus the sum of the residues of f of z at all the poles within the integral, which is exactly what we just stated before. So as you can see, it's not too difficult to see why the residue theorem works, as opposed to some other theorems that might be a little bit tricky, but as you can see, it's not too difficult to understand why it works here. So let's go ahead and figure out how we can calculate residues. So residue calculation is really easy. If z0 is a pole of f of z of order n, now I know this looks really daunting, but it's not too difficult, the residue of f of z at 0, 0 equals 1 over n minus 1 factorial times the limit as z goes to z0 of the n minus 1th derivative of z minus z0 to the n times f of z. Now this looks really, really daunting, but trust me, we're never going to deal with high values of n. I shouldn't say never, but it's very unlikely you're going to deal with high values of n. And really all you need to do is plug in this formula, and this is all very, very basic calculus that anyone in Calc BC could do. Now, the more tricky part is a challenge problem that I'm giving you guys, which is to prove it using the Laurent series of the function about z0. And that seems really difficult to prove, this crazy, crazy formula right here, but trust me, it's a lot easier than it looks. All you have to do is plug in the formula for the Laurent series and show that it actually evaluates to the residue. So, I think you guys should definitely try that. Now, the issue with this is that this requires us to know the order of the pole. And there's something called essential singularities that we talked about before. And we can't use the derivative trick because with an essential singularity, it's equivalent to essentially having a pole of infinite order. So what this is going to look like is, for example, the function e to the 1 over z at 0. If you were to expand it as a Laurent series, you can see that as n grows large, we just have z to the negative n, so eventually we'll get to like z to the negative infinity. And as you can see, we have an infinitely large pole order here. However, that's not actually a big problem for us. We can't use the derivative trick because we can't multiply by z minus z0 to the infinity and take the derivative infinity times and then divide by infinity factorial. That doesn't work. But what we can do is calculate the using the definition of the actual residue. So in this case, it's super easy. We use a Taylor series. So in some cases you may need to use Laurent series, but in this case we can just use the Taylor series for 1 over z. We get 1 plus 1 over z plus 1 over 2z squared. And remember, the residue is simply going to be the coefficient of 1 over z, which is just 1 in this case. So that's super easy. I just think that worked example makes it clear how easy in general it's going to be to calculate the residue at a essential singularity. Now, in some cases, if you have multiple functions multiplying each other, it can get a little tricky, but I think you guys, I don't think there are going to be many situations where you're going to have to do something like that. So just remember, use the Taylor series and directly find the residue by finding the coefficient of 1 over z. So here's our summary. To calculate the value of a contour integral, and this applies to any contour integral for a meromorphic function. And meromorphic functions are not something we've discussed before, but essentially it just means this function, a function being meromorphic just means that it's analytic everywhere except for a set of isolated points. So those are our singular points or our poles where we're going to calculate the residues, right? So some functions that aren't meromorphic are stuff like natural log of z, which has a branch cut, which is something we'll discuss later, or functions that just aren't analytic anywhere, like the modulus of c. So to find the value of any contour integral of a meromorphic function, the first step is to find the singular points. The second step is to find which singular points are within the contour, because you need to only consider those ones. If you consider points that are outside the contour, then you're going to get a value that does not match with your contour integral, and then simply find the residues. So let's go ahead and do some practice problems. So I have a bunch of practice problems right here just for calculating the residues of the function, so I'll go ahead and put those on screen. I absolutely think you guys should try these. So go ahead and pause and try these. Sorry, this right here I kind of screwed up. This says log of z, which is the same as natural log. We just will typically write log in order to, in complex analysis, we usually use log rather than natural log. And I also have some practice problems here on the residue theorem. So all of these are using the contour gamma, which is this curve where we go from negative r to positive r on the real axis, and then we come back on this big semicircle. This is a very important contour, as this is the basis of most contour integrals that are useful to us when we're solving definite integrals, so that's why all the practice problems contain this. So here are 4 practice problems with that curve and with some other curves right here. Go ahead and pause and try these. And I have 4 more practice problems right here. Number 8 is starred because it's an exceptionally hard practice problem. You absolutely do not need to know how to do this, but I think it's a fun challenge problem with an absolutely magnificent result. So go ahead and try these. And I'll show you that number 8, the contour right here, is this curve gamma, which essentially it's enveloping all these residues, all these poles of gamma of z, because there are infinitely many. So we're taking the limit as r goes to infinity, so essentially we're just saying it's going to envelop every single pole of gamma of z. So hopefully you guys tried all of those practice problems and got some practice, and if there's anything you still need help on, I'm absolutely free. Yeah, go ahead and join the Discord and ask me any questions you want, and let's go ahead and go over what's going to go on the next video. We're going to cover a lot of things in the next video, so it might be a little bit of a long video. We're going to cover the estimation lemma, Jordan's lemma, parameterization of straight line integrals, small circle integrals, and possibly branch cuts and points. Oh, sorry, I have a typo there. But I think that I may have to postpone that to a next video, so we may end up having 5 videos in the series. I'm not entirely sure. But yeah, so we're going to cover a lot of things, and essentially by the end of that video, you'll be able to evaluate nearly any contour integral, excluding those with some crazy branch cuts or higher level concepts. But after that, the 4th video is just going to be on strategies for using contour integration in order to actually solve definite integrals. So I hope you guys enjoyed the video. Please let me know if there's anything I can do to improve your experience. Thank you, and I'll see you next time. Hello guys, and welcome to another calculus video. In this video we are going to be covering first of all, this is contour integrate tutorial 3 out of 4. This is where we're going to get into the real nitty-gritty of evaluating contours that are in the complex plane. So in this video we're covering the estimation lemma, Jordan's lemma, parameterization for straight line and circular integrals, small circular calculations, and we're going to dip our toes into branch points and cuts, but we're not going to completely uh, cover those topics. We're going to leave a little bit of that for the next video because it'll make more sense in the next video. So first off, let's talk about what's the point of stuff that we're doing in this video, because I mean there's a lot of different topics that we're covering, right? So what more could we need? We already know how to evaluate contour integrals. So the issue is, let's say I wanted to evaluate the integral from negative infinity to infinity of f of x dx. I'm going to use a contour integral of f of z dz, and this is the path that I'm going to use. Now notice this real axis integral becomes, as r goes to infinity, our integral from negative infinity to infinity. But our contour has another segment, which is this large semicircle that goes from positive r looping back through the complex plane to negative r. So we could write our contour integral as I, right, this integral right here on the real axis, plus this gamma integral. This is a capital gamma, which represents this curve, this upper semicircular curve. So plus the integral over gamma of f of z dz, and this is equal to the overall contour integral, which is just 2 pi I times the sum of the residues. So if we want to actually get the value of I, we can't just use a contour integral. We also have to be able to evaluate this upper semicircle, which is what closes the contour. So that's what we're going to be covering in this video, how to evaluate these curves and others, basically any curve or even straight lines in many cases that we use to close our contours. We need to be able to evaluate those in order to evaluate our original integral. So let's go ahead and jump right into the estimation lemma. So the estimation lemma is very straightforward and pretty logical. So it just says that the absolute value or modulus of the integral over some curve gamma, f of z dz, is less than or equal to m times l. Now m is just the maximum of the modulus of f of z, where z is some point on that curve gamma, right? And then L is just the length of the curve gamma. So overall, we just end up with, the maximum value times the length, right? Which, just some basic reasoning, you can pretty much see that's going to end up being less, or that's going to end up being greater than the absolute value of the integral, or equal to it, right? And then we're also going to be using the triangle inequality quite a bit. This is just something to keep in mind. For two complex numbers, a and b, the modulus of a minus the modulus of b is less than or equal to the modulus of a plus b is less than or equal to the modulus of a plus the modulus of b. And that's very important. So let's just go straight into a worked example, because I think that's the best way to show how to do this. So for our example, we're looking at the function f of z equals 1 over z squared plus 1, and we're trying to show that the integral over gamma of f of z dz, again, gamma is this same curve. I'll always pretty much use gamma just to represent this big semicircle that goes from plus r to minus r in the upper half plane of the complex plane. Again, r goes to infinity. We're trying to show that this goes to 0. So the first thing we're going to do is say that when z is some point on gamma, z can be represented by r times e to the I theta, where 0 is less than or equal to theta is less than or equal to pi. So that just is saying that, that sums up all the possible values of z. So that means that our m is going to be the absolute value of 1 over r squared e to the 2 I theta plus 1, take the modulus of all of that, right? And again, we don't know the exact value of theta here because we're talking about the maximum possible value of f of z over this point. So theta could be really any value in between 0 and pi. So take the modulus on the top and bottom, and then using the triangle inequality from before, we know that the modulus of r squared e to the 2 I theta plus 1 is greater than or equal to the modulus of r squared e to the 2 I theta minus 1, and the modulus of r squared e to the 2 I theta is just r squared, right? Because e to the 2 I theta is just some angle that we're multiplying by. And so since this is greater than this, we take the reciprocals and the less than or equal to sign flips, so we get 1 over the modulus of r squared e to the 2 I theta plus 1 is less than or equal to 1 over r squared minus 1, right? Then we multiply by L. Remember this was M. So I say ML here is equal to this, but really I just less than or equal to, right? So ML is going to be less than or equal to pi r over r squared minus 1. Now the length of this curve gamma, since it's just a semicircle, is going to be pi times the radius, and the radius is r, so that's where we get that. And then remembering that r tends to infinity, we know that this is just equal to 0. So if we know that the ML is less than or equal to 0, we also know that the absolute value, or the modulus, of the integral over gamma is less than or equal to 0. Now, since we're taking the modulus, we know that it's greater than or equal to 0, and it's also less than or equal to 0, so it just has to be 0. And in general, whenever we're picking a contour to do contour integration, we want the integral over gamma to go to 0. So almost every case that you're going to look at, the integral over gamma is going to be 0, uppercase gamma. So let's look at some shortcuts for this. When I actually do contour integrals, I typically will not write out that whole long proof that proves that the value of the integral over gamma is going to be 0. Usually I'll just kind of look at the order and make a little estimation, and I'll say, okay, I've convinced myself that it's going to go to 0, I don't need to prove it to anyone else. And that's something you'll probably see in engineering. So if you're into pure math and stuff like that, I would not suggest doing this, but if you're just trying to solve problems for yourself, I would suggest doing this. So if f of z is some polynomial p of z over q of z, some rational function, then as r goes to infinity, the value of f of z is going to essentially be on the order of r to the degree of p minus the degree of q, right? So that means our m value is going to be on the order of r to the degree of p minus the degree of q. And when we multiply by L is just going to be pi times r, right? So it's going to be, we're just adding one order of r, so just adding one order of r, right? And so that means if the degree of q is more than 1 greater than the degree of p, we can pretty safely argue that ml is going to go to 0, and that means the integral over gamma is also going to go to 0. And that's without doing any real math, just sort of adding up the order of things. And you can also analyze asymptotic behavior for other functions, like for example ln z. Really, as r goes to infinity, ln z is going to go to ln r plus some, I times some angle, but really that's not significant because r is so great. And then when we multiply by ml in this situation, ln z over z squared plus 1, it's also going to go to 0. So let's go ahead and try some practice problems. Keep in mind that the triangle inequality here can be extended to higher numbers. So for example, modulus of a minus modulus of b minus modulus of c is less than or equal to the modulus of a plus b plus c. So here are some practice examples. Go ahead and try these problems. Number 6 is a little bit difficult, so don't worry if you can't figure it out. So go ahead and try these problems. Alright, so hopefully you were able to figure out those problems. If not, you can always ask me about them in my Discord. So yeah, let's go ahead and move on to the next topic for today. Alright, so our next topic here is Jordan's lemma, and this is basically just a sort of truncated, more simple version of the estimation lemma for specific functions. So if gamma is the semicircular arc from plus r to minus r in the upper half plane, now note that this actually doesn't depend on the value of r. So this can be used if you have a smaller semicircle that isn't infinitely large, also to bound your integral. So this tells us that the integral over gamma of e to the iaz, where a is greater than 0, times f of z dz, is less than or equal to pi over a times the maximum value of f of z, the modulus of f of z as z varies along gamma. I don't even really have much practice for this, or an example for this, because it's really just straightforward. You do the same thing as before, you find the maximum of the absolute value, and you just, that's it. So it's much easier than the estimation lemma. So I have a few practice problems for this, but in general, if you don't want to learn Jordan's lemma, I'm pretty sure you can also, for almost every example, you can also use, estimation lemma. Except for this one right here, you wouldn't be able to use the estimation lemma. But so here are 3 examples, and show that the following integrals go to 0. For natural log of z, don't worry about its lack of analyticity, and don't worry about the fact that it's not analytic at some points, because that's just worry about the actual convergence of the integral here. So show that the following integrals go to 0. Alright, so parameterization. So this is a very, very important topic. And this is used also to how to do this to also evaluate, to make the estimation lemma a little bit easier. So sometimes some sections of our contours are straight lines that can be described in terms of normal integrals. And you can also do this parameterization with like circular arcs and stuff, but the main use of parameterization that you really have to learn is for straight lines. So if an integral is in a straight line, so for example, like if you have 2 points in the complex plane and our contour connects those in a straight line, then this is definitely the method you're going to want to use. So you're going to write it, it says write it in as the bounds. That just means write the starting point as a lower bound and the ending point as an upper bound. And then find a substitution z equals z0 plus w times x, w is some complex number, to connect the points, and then evaluate the resulting integral or combine it with other results. So this doesn't necessarily need to be the form of the substitution, but I'll show you some examples and really the significance of the substitution here. So let's go ahead and go straight into an example right here. So we have our f of z is 1 over z cubed plus 1. Our curve, lowercase gamma in this case, is the line running from z equals 0 to z equals e to the 2 pi I over 3 times r. So really this line should be a little bit more to the right there, but it doesn't really matter. And again, r is going to infinity. So notice that this integral is a straight line. So the first step is we're just going to write in the starting point and the ending point as the bounds. So the starting point is 0, and the ending point is r times 2 pi I over 3. Now we notice that if we let z equal x, where x is a real number, times e to the 2 pi I over 3, then x is going to go between 0 and r, right? So that this turns our integral through the complex plane, which is a bit nasty to evaluate, into an integral from 0 to infinity on the real axis, which is really nice. So once we substitute everything in, calculate our differential, which is e to the 2 pi I over 3, we get that our integral is equal to e to the 2 pi I over 3 times the integral from 0 to infinity of 1 over x cubed plus 1 dx. And that x cubed plus 1 just happens because e to the 2 pi I over 3 cubed is just 1. So that's a quick little example here. I have one more example because this is a little bit of a tough topic. So in this situation, our straight line does not start at the origin. So example number 2, we have f of z equals natural log of 1 minus iz over z squared plus a squared. Now, this line goes from z equals I plus epsilon to z equals I r plus epsilon. And of course, we're taking r goes to infinity and epsilon goes to 0. So this is a visualization of the line here. It's not a very good example because I didn't fill in everything, but essentially we're talking about something that's just infinitesimally to the right of the imaginary axis, and it runs up from I to I infinity. So, of course, the thing we're going to do as we did in the past ones is we're going to write in the bounds. So I plus epsilon as the lower bound and IR plus epsilon as the upper bound right here. Then we notice, see how these are, actually I'll give you guys a moment. You should try and figure out the substitution that you should make to turn this into a real axis integral by yourselves. Now if you were able to figure that out, you would have found that z equals ix plus epsilon, where x is going to go between 1 and r. And the reason we're making this substitution is, as you can see, we have I plus epsilon, IR plus epsilon, that's I times some number plus epsilon, where that number is real, right? So that's the substitution we're going to make. dz is going to be I dx, and then that allows us to go ahead and plug in everything right here. We get an integral from 1 to r, and then we let r go to infinity and epsilon go to 0. And we get I times the integral from 1 to infinity of ln 1 plus x over a squared minus x squared. Very nice. So now let's go ahead and look at some practice problems. So for these practice problems, you don't actually have to evaluate the integrals, you just have to represent the line integrals in terms of an integral over the real axis, remembering that r goes to infinity and epsilon goes to 0. So here are our 5 examples right here. Alright, hopefully you were able to figure out all those practice problems. Let's go ahead and move on to the next topic. Okay, now we're going to talk about small circle integrals. So small circle integrals are a little bit of an interesting topic. Usually we have small circle integrals when there's a certain point that we want to avoid in our integration, but it's sort of like in our way. So for example, this point may be a pole or it may be a branch point. And so essentially we'll have to integrate over the point. But again, we can't integrate over points like this, So what we do is we imagine that we integrate in a small circle around the point, and then we take the radius of that circle, which we call epsilon, we let epsilon go to 0. And so that's essentially how we get small circle integrals, and the ways to evaluate them vary depending on the type of point that we're around. So for example, here I have a formula that helps us if our point is a first order pole. So if gamma is a positively oriented, remember positively oriented means going in the counterclockwise direction, circular sector of angle theta and radius epsilon, remember epsilon is going to 0, and f of z is analytic in the neighborhood of f of 0, meaning f of z doesn't have any poles near f of 0, and by near I mean like infinitesimally close, or branch points or branch cuts or anything like that, then the integral over gamma of f of z over z minus z0 dz is going to be I times theta times f of z0. And a way you can kind of internalize this is, you can imagine if we let theta equal 2 pi, then we're really going a full circle around that point z0, and so since we're going a full circle around, we're really just going to get 2 pi I times the residue at z0, which is just exactly this. If we plug in theta equals 2 pi, that's going to be just the residue at that point. And so if we go a certain percentage around that circle, we're going to accumulate a certain percentage of that residue. So that's where this comes from. This formula is not difficult to prove, so if you guys want to try and prove it, I definitely suggest it, but it's absolutely not something you need to do. So let's go over an example here. This is actually an example from one of my more recent videos. So our function here is e to the I pi z over z cubed plus 1 dz. And we're integrating in a small circle of radius epsilon around the point z equals -1. Notice that we're going in the clockwise direction, which is the positively oriented direction, and also our angle theta is going to be pi because we're going a perfect semicircle, so that's half a circle, right? Now, in order to find, clearly we're going to have a pole here, because if you plug in z equals -1, you get 0 on the bottom. So when we factor everything, we can get that f of z is going to be equal to e to the I pi z over z squared minus z plus 1. And then all we have to do is plug in our formula. So remember, it's going to be I times theta times f of z0. In this case, z0 is -1. So I times theta is just going to be I times pi, and f of z0 is going to be e to the -I pi all over 3. So overall, our answer is going to be -I pi over 3. And you can see that in one of my recent videos. However, sometimes we aren't actually going around a pole. Sometimes we're going around what's called a branch point. Now we'll get to branch points later in this video, and we'll cover them fully in the next video. However, this is not really, this is also an important topic, because we can never integrate over a branch point, so we always have to go around it. So that's probably the main reason why we're going to be using these small circle integrals. Now, almost always these small circle integrals are going to go to 0 because, well, you'll see why. And the main way to do these is either you can use parameterization or you can use the estimation lemma. So in this case, I'm using the estimation lemma because it's a little bit more familiar to us. So in this case, we're going in a small circle in the counterclockwise direction around the point z equals 0. And we have ln z over z squared plus 1 dz. Now we're going to use the ML inequality, right? So m is going to be the maximum value of ln of epsilon e to the I theta over epsilon squared e to the 2I theta plus 1, because any point on this curve right here can be represented by epsilon e to the I theta for some theta between 0 and pi. And then using the absolute value right here, again using the triangle inequality right here, we get 1 minus epsilon squared. We get that it's going to be less than or equal to natural log of modulus of natural log of epsilon plus 2 pi. Actually, this doesn't even need to be 2 pi. This could be pi. Again, just using the triangle inequality on both the top and bottom. And then that means that ml, remember that L is going to be pi times epsilon, is going to be less than or equal to pi epsilon times the modulus of natural log of epsilon plus 2 pi. Again, this can just be pi. And on the bottom, this should be 1 minus epsilon squared, not epsilon squared minus 1. Don't worry about that. But anyway, as we take the limit as epsilon goes to 0, this epsilon on the top is just going to dominate over everything, and so it's just going to be equal to 0. So almost every situation, these integrals are just going to go to 0, so you don't really need to worry about it that much. But always just go ahead and do a quick check. It's always good to, just show this just to be sure, because if you make a mistake now, it might be hard to fix it later. So here's some practice. They're all going to be over the same place right here. So some of these are going to be, these are just different small circle integrals right here. Some of them might go to 0, some of them the theorem that we stated before. Anyway, go ahead and try them. You might have to use. Alright, so next topic is by far the toughest one, and it's going to be a little bit hard for me to explain it, but I'm going to try my best. So some functions like ln z and square root z are multi-valued, and what this means is depending on how we define natural log of z, or typically you'll write log of z, and square root z, or any fractional power of z, there's different ways that we could define it, and they could have different values at the same point. For example, for square root z, there's always two possible numbers which you could square in order to get z, right? So that's why square root z is a little bit tough to define. And at the same time, e to the 2 pi I equals 1, which causes problems with ln z, because if you think, okay, what's natural log of z, or natural log of 1, well, you would just say 0, right? But I'm telling you e to the 2 pi I also equals 1, so natural log of 1 could also be 2 pi I. So that doesn't really make any sense, and again, using this fact, it could be 4 pi I, it could be 6 pi I, it could be 8 pi I, and stuff like that. And no matter what number you're taking the natural log of, you're going to have this problem because, again, e to the 2 pi I equals 1. So in order to fix this problem, what we do is we fix the argument. Now, the argument just means the angle, which you should probably know if you're on this video. We fix the argument of a complex number to an interval between some angle alpha and some angle alpha plus 2 pi. Most commonly, this means that our argument is going to be between negative pi and pi, but depending on the function in the contour, we may choose a different branch cut. So this is called a branch cut. We're going to define where our natural log is going to jump. So here's what I mean by that. So in this situation, we have theta equals 0 going to be right here. We're looking at the situation where negative pi is less than the argument of z, which is less than pi. So if we move in the counterclockwise direction, our angle is going to increase until it reaches pi. And if we go in the clockwise direction, our angle is going to decrease until we get to negative pi. But notice where these 2 points meet, the argument is not very well defined because, well, right below this line, our value is negative pi, and right above it, our value is pi. In fact, we completely jump over this line, right? The value changes by 2 pi when you cross this line. And since the argument is an important, it's part of the natural log, essentially. ln z is equal to the natural log of the modulus of z plus I times the argument of z. So this discontinuity that exists in the argument of z also exists in the natural log of z. And this is why the natural log of z is neither an analytic function nor a meromorphic function, because it will never be continuous over this entire line. So here's another example of a branch cut we may choose. 0 is less than the argument of z is less than 2 pi. Now in this situation, theta is going to increase going counterclockwise in a full circle, right? But again, when we reach this full circle, if we want to keep going, our argument is going to change by 2 pi. And another common branch cut that we might pick is negative pi over 2 is less than argument of z is less than 3 pi over 2, which means that our branch cut will run from z equals 0 all the way down to negative I infinity. So each branch cut is going to start at a branch point. Now the branch point is usually going to be z equals 0 for ln z and run out to infinity. Now, of course, if you have the function like ln z plus 1, then your branch point is going to be whatever makes the input of ln z 0. So it would be negative 1 in that case. When we move over the branch cut, the function's value changes suddenly, causing a discontinuity, so the function is not analytic in the region. I already discussed that. For that reason, we have to carefully place branch cuts so that they are outside of the contour, because otherwise we wouldn't be able to use the residue theorem. Here's another example here with square root of z. Now, when you take the square root of a function, its argument is halved, right? Just because of the way that exponents and powers work. However, when we say that we have the angle, what does that really mean? Well, if we define our argument of z between negative pi and pi, that means that everything, it's always going to move to the right? Because, our angle is pi over here, so it would go to pi over 2. It's always going to move this way. And when we're below the branch cut right here, it's always going to move this way. However, if we defined our branch cut somewhere else, like for example, if we defined our branch cut on the positive real axis, then a point right here would get mapped all the way back here when we take the square root, which is totally different behavior, which shows that the branch cut is incredibly important because it changes the behavior of square root z. Now, fractional powers also have branch cuts since calculating them requires dividing the angle, and this can get very, very hairy. So the way that we make this a little bit easier is we define z to the p when p is not an integer as e to the p ln z. So now these fractional powers are in terms of natural log of z, so we can just use the same branch cut for natural log and for fractional powers, right? Otherwise, we would have to deal with multiple branch cuts, which you guys will soon learn is very, very annoying. Oh, sorry about that. So there are two things to keep in mind when choosing a branch cut, and we'll talk about choosing a branch cut in the next video a little bit more. The first thing is that we need to make sure the branch cut lies outside of the contour, and that's pretty straightforward because if the branch cut is inside the contour, we can't use the residue theorem. The other thing that's a little bit tricky sometimes is to ensure that your function still evaluates to the original function. So an example of this is, let's say we wanted to integrate a function with natural log times some other function, right? So f of z equals natural log of z times g of z, where g of z is going to be a meromorphic function, so it's well behaved, but it has some poles. The branch point is going to be z equals 0, which I've marked on the graph here. We want to use this contour. It's going in the clockwise direction, and notice that this is our semicircular contour that we've used for pretty much everything, but the exception here is that we have this little indent in our contour. And this is going to be one of our small circle integrals, which I talked about further. So given that the small circle integral happens because of a natural log, based on what I've told you, do you think the small integral is going to have a value that it contributes to the integral, or do you think it's going to go to 0? Now, hopefully you were able to guess that it's going to go to 0 because small circle integrals with natural log almost always go to 0. Now, the trouble here is we have to pick a branch cut for natural log of z. And there are 4 options that I have detailed here. Let me zoom out a little bit. I want you guys to try and figure out which one we should use. Keep in mind these 2 rules right here. And remember that our original problem was evaluating an integral on the real axis of f of z. So let's go over each of the options one by one. So option A, 0 is less than or equal to the argument of z is less than 2 pi. Now in this situation, we have to look at, okay, where's our branch cut going to be? Well, our branch cut is going to be on the positive real axis right here. And the problem with that is that our contour integral actually goes right over the positive real axis. So that's no bueno. That's not good. Because then we won't be able to use the residue theorem, and we might get the wrong value for our integral. So let's look at option B. The most common choice of branch cut is going to be negative pi is less than argument of z is less than or equal to pi. However, this example doesn't work because our integral, again, goes over the negative real axis, which is exactly where the branch cut would be if this was our branch cut, because as you can see, right here would be the angle pi or the angle negative pi, so that's right where our branch cut is going to go. Now option C looks very nice, because if we look at where the angle 3 pi over 2 and 7 pi over 2 meet, that's right here on the negative imaginary axis, which is nice and far away from our contour, which means that we'll be able to use the residue theorem to evaluate the integral. However, notice that for C, this interval that we have right here does not include the argument of z being 0. And a fundamental assumption of the natural log is that the argument of, the natural log of a real number, a positive real number, is going to be also a real number. I mean, think about it. When you take natural log of any positive real number, you get a positive or negative real number out of that. You don't get an imaginary number. But if we define our argument with this definition, a real number would have an argument of, I guess it would have an argument of 2 pi, right? So that means that the natural log of 2 would be the real part of natural log of 2 plus 2 pi I, which doesn't really make any sense in the context of what is a natural log. So this is not a good option either. And that means that D is actually the branch cut that we want to use. Because it has the same, the branch cut is located in the same place. It's located from z equals 0 and it goes to z equals negative I infinity. The difference is that in this case, the definition of the natural log on the real axis, the positive real axis, stays the same as our usual definition, which means that our function still evaluates to the original function, which means that both of these criteria are met. So that means this is the right branch cut to pick. So we're not going to do any practice problems for this because we're going to go over this topic more in part 4. But yeah, so next video we're going to go over common contours. So we're also going to go over how to choose a contour, and symmetry, bounding, and branching. Those are basically methods of choosing a contour. We're going to talk about what functions are nice for contour integration. So when you get an integral problem, how to analyze, okay, is this going to be good for contour integration, or is it going to be, or am I going to have to use another method? And we're also going to go over how to modify a contour and choose a branch. So anyway, I hope you guys enjoyed the video and I hope you learned a lot. Remember, you can always join my Discord to ask me any questions you might have. If you watched through to the end, thank you so very much, because I know that this was a very, very long video. The first time I recorded this, it actually went to 40 minutes. I'm not sure how long it is this time, but I'll give it a check. And yeah, so thank you for watching. Stay tuned for part 4, and if you're watching this whole series, thank you very much, and I hope you learned something. Thanks, see you next time. Hello guys, and welcome to the grand finale of the contour integration series on this channel. If you guys have watched all the previous videos, or maybe you're watching this all as one video, I thank you very, very much for all the support of the channel, and I hope you really learned a lot about contour integration, and hopefully after this video you'll be ready to use it for whatever it is you are trying to solve. So again, thank you all for all the support, and I hope you enjoyed this series. Anyway, let's go over what we're going to cover in this video. We're going to cover common contours that we use for integration, symmetry, bounding, and branching, which is 3 important criteria that we use to decide what type of contour we're going to use to integrate. We're going to cover how to choose what kind of contour you're going to use to integrate, and how to modify that contour so that it fits your exact needs for that exact function and that exact integral. So without any further ado, let's jump right into it. This is going to be a more fun video, so let's go ahead and get started. So first, I'm going to go over the contours that are covered in this video. We will be covering the semicircular contour, the circular sector contour, the keyhole contour, the circular contour, and the box contour. Now, there are some contours that we won't cover because they're a little bit more advanced or they're just not useful for our purposes. So the Hankel contour, which is used in complex analysis, the dog bone contour, which is used when you have multiple branch cuts that run in opposite directions, the T-bone contour, which is for similar situations, and contours involving residues at infinity. Now, we did not cover residues at infinity, so I'm not going to be discussing those contours, but if you would like to learn more about contour integration after you finish this video, I definitely suggest searching up some of these contours and figuring out how to use them in integration. So let's go ahead and get started. The first thing we want to cover is how do we choose how to create a contour? And essentially, there's 3 things that we should be considered when we're choosing a path for our contour integral. The number 1 absolute most important is symmetry. If our function has some symmetry along some line or curve in the complex plane, use that to your advantage in order to close your contour. This is typically ray symmetry or parallel symmetry. Now, what we mean by ray symmetry or parallel symmetry is essentially if you have multiple lines that come out from the origin that have some sort of similarity on them. So, for example, if your function acts very similarly on the line running from x equals 0 to positive infinity, and it looks very similar to that on the line from x equals 0 to x equals I infinity, then you should probably be using that symmetry to your advantage in order to close your contour, because, of course, we want to make evaluating a contour integral as easy as possible, and so that means we need to make sure that as many parts of our integral as possible are going to be easy to either evaluate or to turn into a form that's already evaluable, or prove that they go to 0. So that leads us into our next important topic, which is bounding. So you want to make sure as many parts of your contour as possible go to 0, because that means less sections you have to evaluate. So you'll see that some of our contours will purposefully spend a lot of time looping around close to infinity, because close to infinity in general our functions will go to 0. and then that makes our contour integral much easier to evaluate. And branching. So sometimes we'll have to modify our contour or choose one specifically due to branch cuts in our function, and that'll make a little bit more sense once we get to some of the other contours that we're going to cover in the video. So let's go ahead and get started. So the absolute go-to is the semicircular contour. This is by far the most useful contour that shows up in all sorts of situations. Now this contour just looks like a big semicircle. I have two contours here, the green one, which is the semicircle in the upper half plane, and the red one, which is the semicircle in the lower half plane. So depending on the value of your function in the upper and lower half plane, you might want to choose the upper half plane or the lower half plane. Again, you just want it to go to 0 on this outer arc right here, so you may have to choose either the upper or lower. And this is generally used for the integral from negative infinity to infinity of f of x dx. Now let's talk a little bit more about the motivation of this. So obviously, right, we have our real axis integral right here. We absorb all the residues right inside the contour, and if our function goes to 0 on this curve capital gamma right here, then our contour integral is really easy to evaluate, and that's kind of the point of choosing the semicircular contour. So it's incredibly simple, and if the function decays at infinity, then the gamma integral may go to 0. It also contains all the residues in the upper half plane or the lower half plane if you're using that version of the semicircular contour. Also something to note, if you put your semicircle in the lower half plane, then the contour you use will be oriented negatively, which means that you'll have to take into account the fact that when you use the residue theorem, you'll get negative the value of your contour integral because of the negative orientation. And the types of functions that this works well with is rational functions, trigonometric functions, logarithms. Of course, you will need to make some modifications due to the branch cut, and any bounded function in the upper half plane. So basically any function that's bounded in the upper half plane, you can go ahead and just plug in this contour and it'll work out very nicely. So in general, we're going to use a lot of rational functions with this, but here are some examples. P of z over q of z just means a rational function of z. And then when we multiply by e to the iz, that allows us to incorporate some trigonometric functions in there. And again, it's just really, really helpful because those trigonometric functions, or rather not the trigonometric functions themselves, but e to the iz is bounded in the upper half plane. Natural log of z and inverse tangent of z also works quite nicely. So let's go over a quick example for a very, very simple function. So I'm not going over every single part of this contour integral because in the past video you guys learned how to do many of the methods that I'm showing here. So if you guys want to go ahead and prove these things, then please do, right? So the example we're doing here is the integral from negative infinity to infinity of cosine of x over x squared plus 1 dx. Now, of course, we want to convert everything into a nice little complex analysis form, so this is going to be the real part of the integral from negative infinity to infinity of e to the iz over z squared plus 1 dz. So we're going to use a contour integral of the same function, and we're going to just use the upper semicircular arc. And this is really nice because we capture this residue at z equals I. We have on the real axis, this will be equal to our original integral, or rather, I guess it'll be equal to, so it'll be equal to our this integral right here on the inside of the real part function. And then on this upper semicircle, we can use Jordan's lemma in order to show that it goes to 0. So we know that the contour integral overall is going to be 2 pi I times the residues of f of z, where f of z is this function, at z equals I. And it's also going to be equal to our integral over the real axis, which we call I, plus the integral over gamma. And you guys can go ahead and show that the gamma integral goes to 0 using Jordan's lemma. And this means that 2 pi I times the residues equals our integral over the real axis, which also equals this integral right here because the imaginary part is going to be 0. So see, in just one slide with some very, very straightforward methods that you guys already know how to do since I taught you them in previous videos, we have proven this absolutely crazy integral, which would be very, very difficult to solve with any other method except maybe the Laplace transform, but even so, that would take quite a few steps to be able to solve. So that's the appeal of the semicircular integral. It makes contour integrals incredibly easy. Another integral or another contour that we may use here is the circular sector contour. So notice that we sort of trace out the integral from 0 to infinity, and then we go back in this semicircular arc, but we won't necessarily make a full semicircle here. That depends on our value of theta. If theta equals pi, then we just get our semicircular integral, which means that the semicircular integral is actually a special case of the circular sector contour. And notice that theta can be anywhere, anything from 0 to 2 pi, and this can give us a lot of different options for our integral. And this is typically used for the integral from 0 to infinity of f of x. Now, the main appeal of this type of contour is if your function has some sort of radial symmetry, and you'll see what I mean by that. So, So it's appealing when we have power functions of z, and the reason for this is because if f of z is z to the p, then if we replace z with z times e to the 2 pi I over p, we get f of z again. And what this means is when we're replacing z times e to the 2 pi I over p, that means that the values of the function over this line will be the same as the values of the function over this line, since all we're doing is multiplying everything by e to the I theta, which in this case theta could be 2 pi over p, right? And so the appeal of this is that when we parameterize the path back from the circular arc, our integral can be expressed in terms of the real axis integral I. So this works well with rational functions, power functions, and logarithms. So here are a few examples of different functions that we can use. Again, not too many examples, but as it gets more complicated, you can figure out some other examples there. So here's a quick classic example. If we wanted to calculate the integral from 0 to infinity of 1 over x cubed plus 1 dx. Now, if this were 1 over x squared, we would just go ahead and say, okay, well, 1 over x squared is an even function, so we can write this as 1/2 the integral from negative infinity to infinity of 1 over x squared plus 1 dx. But because it's x cubed, we can't do that, and that means we can't just use our semicircular integral. So instead, we notice f of x is the same as f of e to the 2 pi I over 3 times x. And again, here we can't switch this to the integral from negative infinity to infinity, which is very, very sad, but we can use this circular sector integral. So if we consider the contour integral over the circular sector of 1 over z cubed plus 1 dz, we have this I1, this I, we have a pole at z equals e to the pi over 3, and we have this gamma contour, of course. So the integral of f of z dz is going to be the 2 pi I times the residue at that point, and it's going to be equal to our integral I, which is the integral over the real axis, plus this integral over I1, plus this integral over gamma. And using the methods that I taught you in the last video, you can show that the integral over gamma goes to 0 using the estimation lemma. You can show that the integral I1 turns into negative e to the 2 pi I over 3 times I using parameterization. And so this means that I times 1 minus e to the 2 pi I over 3 equals 2 pi I times the residue at this point, right? And so then all you have to do is some simple algebra and analysis to get to our answer of I. So our next contour is a little bit interesting and it looks a little silly. And this is the keyhole contour. So the keyhole contour is principally for when we have a function with a branch cut. Running from the center right here all the way out to infinity. And what we do is we integrate just above the real axis. We go in a full circle all the way around in this large gamma contour. Then we come back just below the real axis. And then we go around in a tiny infinitesimally small circle right here around the point z equals 0. And essentially what will happen in many situations is because we have our branch point at z equals 0 and our branch cut running from z equals 0 to z equals positive infinity, this integral on the just above the real axis and just below the real axis are going to interact with each other a little bit. Typically, they'll just be off by a factor, or they'll just be subtracting. They'll be off by like a single term, and so since they're running in opposite directions, we're going to subtract them from each other, and we'll get a much simpler integral. And so the appeal of this is, whenever we have a nice little branch cut right here, this keyhole contour is really nice because it completely avoids that, and it still gives us this nice circular action, which allows us to not have too many parts of an integral that we need to evaluate. So Pretty much, it's the go-to contour for when you have a branch point at z equals 0 and your function is not super simple. Because if it is super simple, chances are you can just use the semicircular integral. So the contour is closed, it avoids all the branch cuts, and both straight line integrals are infinitesimally close to the real axis, which means that the argument along the entire upper integral is 0, and the argument along the entire lower integral is 2 pi because of that branch cut that we place right there, which usually will lead to some nice symmetry, and I'll show you an example of that in a moment. Now, this trick is a little bit confusing, but we have what's called the phantom log trick, and what we can do is we can multiply a rational function or even a function with natural log of z in it by natural log of z, and then we integrate over the keyhole contour. And what happens is on the upper keyhole contour, natural log of z will just turn into natural log of x. But on the lower contour, natural log of z will turn into natural log of x plus 2 pi I. And then when we subtract these two integrals from each other, the natural log of x will cancel, but the 2 pi I will remain. And what this means is that essentially, once we multiply by this natural log of z, it ends up disappearing and being replaced with the 2 pi I. And so this allows us to integrate a lot of different functions over this keyhole contour. And even if these functions don't have any nice symmetry, or maybe they have singularities on the real axis, the keyhole contour is just the only place where it's going to be easy to integrate them. And it's a little bit hard to explain the phantom log trick, but if you're really stumped, you can always try multiplying a function by natural log of z and integrating over the keyhole and seeing how things cancel, and it may just work out for you. And in general, the keyhole is going to work with anything that decays to 0 as r goes to infinity and has a single branch point at z equals 0. If it has another branch point somewhere else, the keyhole contour won't work out very well. So here's an example right here. We have a pretty straightforward function, integral from 0 to infinity of z to the p over z plus a times z plus b, which is going to be equal to I, and a and b are greater than 0, p is between -1 and 1. So this is our keyhole contour right here. We have poles at z equals minus a and z equals minus b. I don't know why it says positive here, but I didn't really draw the keyhole too well here, but it's the same as this keyhole right over here. The exact same contour. And then the point here is we get that our integral is going to be 2 pi I times the sum of the residues, and it's going to be equal to I1 plus I2 plus our lowercase gamma integral plus our uppercase gamma integral. And both of the gamma integrals go to 0 using the estimation lemma, which you can go ahead and prove right now if you want. And then when we use parameterization, we find that I1 is just going to be equal to I, and I2 is going to be equal to negative I times e to the 2 pi ip, which means that once we calculate the residues, we just need to divide by 1 minus e to the 2 pi ip, and we get the value of I. So this next one is very different from what we've seen. We've seen a lot of nice little circles and symmetry that way, or functions that go to 0 just because we have that nice circular arc. But this is going to be a go-to when functions don't go to 0 on that circular arc, and they have other types of symmetry, which we'll discuss. This is the box contour. So with the box contour, we're running from negative r to positive r, which is pretty much just going to be negative infinity to positive infinity. Then we go upwards on the imaginary axis, or not on the imaginary axis. We go upwards in the imaginary direction to plus r plus k pi I to minus r plus k pi I, and then we close the contour back down. Now, I'll go ahead and try to explain the appeal of this contour. It's a little bit confusing, but as you might expect, the key word here is symmetry. The exponential function, and by extension trigonometric and hyperbolic functions, have nice symmetry across parallel lines shifted over by 2 pi I. And this means that e to the 2 pi I, because e to the 2 pi I is 1, if we shift our function over by 2 pi I, and our function is completely composed of just e to the x, it's just going to be the same exact function. And sometimes we'll shift it over by pi I instead, because e to the pi I is -1. And so this means when we're using exponentials or hyperbolic functions, which don't go to 0 as r goes to infinity, the only way to close the contour is using these nice lines, because otherwise we'll just end up with some other integral that we have to solve with whatever path we take to close the integral, right? The integral, or the contour has to be closed in order to use the residue theorem, And the only really good way to close the contour is to use some symmetry so that we can combine the path that we use to close the contour with our original path. So the way we do this is we try making a big box where the top and bottom paths are k pi apart in the imaginary direction. Depending on your function, k may be 1 or 2, and even in some cases 1/2, maybe even like 3 or something like that. I don't really know how that would be helpful, but yeah, so that's the idea behind that. You can experiment by plugging in different values of k to see what gives you nice symmetry. So just plug in different values of z plus k pi I to see what gives you symmetry in your function. So here's a quick example right here, very classic example right here. We have the integral from negative infinity to infinity of e to the ax over e to the x plus 1 dx, where a is between 0 and 1. So we end up with a contour integral, and we're going to be going over the box contour. In this case, our k is equal to 2. So we just have this big box, go up by 2 pi I, go all the way back to negative r, and then go down by 2 pi I again. And we have a pole at z equals I pi because e to the I pi equals negative 1. So, of course, our contour integral is just going to be equal to the residue at pi I, and it's going to be equal to c1 plus c2 plus c3 plus c4. And in this case, c1 is just this line right here, c2, c3, and c4. Now, c1 and c3 go to 0, which you can prove using the estimation lemma. And then using parameterization, you find that c2 and c4 are very, very similar. c4 is just equal to I, and c2 is going to be equal to negative e to the 2 pi I a times I. And so all you have to do is divide by 1 minus e to the 2 pi I a, and then you get your value of I right here. Okay, and go ahead and try that one if you want. All right, so this is a little bit of an interesting one. This is very different from the rest of our contour integrals because it comes directly from a substitution rather than taking our function through the complex plane. So this is just a simple circle. That's all it is. And you'll usually see it denoted by the contour integral over the modulus of z equals r. And of course, it's assumed that you're going in the counterclockwise direction. Now this only happens in a very specific type of integral, which is when we have the integral from 0 to 2 pi of f of sine of x and cosine of x dx. And we can rewrite this as g of e to the ix because sine of x is e to the ix minus 1 over e to the ix all over 2I, and cosine of x is e to the ix plus 1 over e to the ix all over 2. Something else to note here is that this function of sine of x and cosine of x, it could just be some arbitrary function of e to the ix. In general, you'll see it in forms of sine of x and cosine of x, but I've had some situations where it's just written in terms of e to the ix. And essentially what we do here is we substitute z equals e to the ix, and we get that dz over iz equals dx. And what happens is if you actually track the path of e to the ix, where x varies from 0 to 2 pi, you find that the starting point and the ending point are the same, obviously, because e to the 0 is the same as e to the 2 pi I. But if you actually track the path, you'll find that it just follows this little circle. It starts at theta equals 0, and then it goes around in a full circle right here in the counterclockwise direction, reaching theta equals 2 pi. And that is pretty much just the definition of a closed contour in the complex plane. So this means that it's actually equal to the contour integral over the modulus of z equals 1 of g of z over iz dz. So let's look at an example of how this works out. So this is our function integral from 0 to 2 pi of cosine squared of x over 3 plus 4 sine of x dx. Then z is going to be e to the ix, and dz over iz is going to be dx. And this just ends up being the contour integral over z equals 1. And then, just using the identity with cosine of x and sine of x, we get this nice expression. That's actually not a very nice expression, but it is an expression. And essentially, you just have to simplify everything, factor the bottom, find the poles, and then plug in the residues. I'm not going to do all that busy work, but if you guys want to go ahead and try that, absolutely be my guest. So let's move on to our next contour. Oh, looks like we have reached, that is all the contours that we're going to talk about today. So now I'm going to talk about irregular contours. So essentially every problem is different, and some of them will have unique contours that don't fall into any of the categories mentioned here. So just play around with your function, look for symmetry, look for places where it's well defined in the complex plane. I mean, honestly, like some problems, they're just going to have contours that you would never even think of, and that's okay because contour integration is, a very advanced topic. You can't expect everyone to guess, oh, what if I try this random contour? But, it's always worth a shot just trying something. So I have an example here from QN Cubed, absolutely a brilliant YouTuber. I learned a lot of the stuff that I know from him. And I was just looking at this problem the other day, and he takes this integral from -1 to 1 of inverse tangent of x times ln 1 plus x squared over x all over x plus 1 dx. And he does some manipulations, and I was able to follow most of it, but he ends up with this contour integral that goes from like e to the I pi over 4 to e to the negative I pi over 4, and then it like goes back in a circular arc, and it's like, this is the weirdest looking contour integral ever. I mean, like, who would even think of this? But you just have to sort of look at your function, look, oh, these 2 points are in the unit circle, so what if I connect them back using a contour through the complex plane, right? So it's just, it's just practice and, trying everything that pops into your mind, because you'll never know if you might just come up with a genius idea and have to try it. And with that, we have one more topic right here. We're going to talk about modifying contours. So most contours that we're going to use are going to look pretty much similar to the ones that were shown, but they're going to have slight modifications because every function is different, and that means that every contour is going to be a little bit different. So if our path runs directly over a singularity or branch point, the only thing we really have to do in that situation is make an infinitesimally small circle to go around it. And you'll see this in a lot of different contours. I'll show you an example. If you think about the keyhole contour, that's pretty much what we're doing there. We're just having an infinitesimally small circle just to go around that branch point at 0, and that's that gamma integral right there. And another thing that to keep in mind is if your function has a nasty branch cut that's getting in your way, you can always try to deform your contour around the branch cut. And I'm going to show you an example where it looks like a really silly deformation, but it works out perfectly. And so there's always a fair chance that the integration will still succeed, even if your contour looks a little bit silly. I mean, it's always worth a shot because contour integration in general is really easy to check if your function is still going to be integrable. So let's go ahead and take a look here. I want to integrate this function f of z ln z dz. I didn't rate it here, but I want to integrate it from negative infinity to infinity, I guess, in this situation, or maybe 0 to infinity. I don't know, we'll see. But anyway, I'm trying to use this semicircular contour here, but natural log of z has a branch point at z equals 0. I've chosen the branch cut to run from z equals 0 to z equals negative I infinity because that way it stays outside of our contour. But again, the branch point right here is in the way, and we cannot integrate over a branch point. So all we're going to do is deform it. We just make an infinitesimally small circle around the branch point, and voila! Now the branch point is completely out of our path of integration. This small circle doesn't actually change the value of the integral. In general, obviously it depends on your function, but chances are this will just go to 0 anyway, and that's all we had to do. We just had to make a slight modification right there. And the same would be true if instead of natural log of z we had some sort of pole in this situation, right? So here's another deformation that's very common that you should get used to. First of all, know that inverse tangent of z can be defined in the complex plane as I over 2 times natural log of 1 minus iz over 1 plus iz. And then we have, if we're trying to integrate f of z times inverse tangent of z from negative infinity to infinity, of course, and we want to use the semicircular contour right here, if we choose the principal value of the natural logarithm, then we're going to have a branch point at z equals negative I, and it's going to run down to negative I infinity. And this really isn't in the way of anything, but as you can see here, this branch cut running from I to I infinity of the other natural logarithm right here, I mean, it slices straight through our contour, and it's completely in the way. And turns out, all we have to do is deform our contour a little bit. We literally just change the contour so that it just goes around that branch cut, which looks really silly. I mean, I just made it go down and then around in a circle and then back up. I mean, who would think that that works? But that's actually a contour that I used twice in recent videos because it just works out very nicely in the end. And so, even though this looks like a very silly deformation, it works out quite well. So, try every deformation to get rid of those branch cuts that are making your day insufferable, right? All right, so I believe that is everything we have to cover. Yep. That is all you need to know about contour integration to get started on working on some awesome definite integrals. So I have a lot of practice problems here because now we've basically learned everything about contour integration that we know that we need to solve these problems. So let's go ahead and do some practice. So here are the first 6 practice problems. Go ahead and pause and try them. Your goal is to pick a contour which can help you evaluate the definite integral, and then go ahead and solve for the value of the definite integral. All right, hopefully you've given those a look. Let's go ahead and try another example right here, another few examples right here. These are a little bit more difficult in general. Also, if you weren't able to figure out number 5, a nice contour for this, I would suggest trying the phantom log trick, which I mentioned earlier in the video. So let's go ahead and look at the next set of practice problems. These ones are a little bit more difficult, but I think you guys can figure them all out. Alright, hopefully you gave those problems a try, and if you weren't able to figure some of them out, I'm always open in my Discord, which you should go ahead and join, just to discuss, and to see if there's anything that I can help you out with. So, I have one more bonus problem, which I think is fun. The bonus problem is to find a definite integral, which can be evaluated using the Pac-Man contour right here. I do know of a function that can be, a few definite integrals actually, which can be evaluated using this Pac-Man contour, so go ahead and give that a try if you like. But if not, thank you so much for watching my contour integration series. It has been an absolute pleasure to be your teacher, and I hope you continue to watch videos on my channel if you find them helpful. Thank you again, thank you so much for watching. I hope you learned something. I'm always happy to help, and yeah, hope you enjoyed the video, and I'll see you next time.